Hi friends, in this video let us discuss about viscosity, because viscosity is one of the important component in fluid mechanics. So like salt in the food, the viscosity is very important in the fluids. So if there is no viscosity, then the science about the fluid mechanics would have not been this much interesting, because in fluid mechanics we come across a lot of interesting phenomena, so because of the viscosity. So viscosity exists only in real fluids that we know well. So we'll see how the viscosity is helping, or okay, how to understand the viscosity in a better manner. Okay, so first of all, we know viscosity is nothing but internal resistance. If we are having fluids, within the fluids there is a viscosity. So water is having lower viscosity, so we can say, and engine oil is having little higher viscosity. So viscosity defined by the internal resistance. How much internal resistance offered while just operating or while coming across the applications. First, let us see about viscosity, and then we'll talk about further. So viscosity, as we said, it is nothing but the internal resistance. So internal resistance in fluid mechanics. So in internal resistance, nothing but we used to take it as the fluid as the layer by layer. That means fluids are in fluid mechanics. The fluids are we used to consider as the layer by layer. So like this, the fluids used to fluids flow used to be like a layer by layer. So if you consider any of the two layers, in the fluid flow, then this layer has the different velocities. Each layer has the different velocity. This layer will be having one velocity, and this layer will be having another velocity. So that is how we are coming across one term called relative velocity. Because of the internal resistance, so this layer offers a resistance on the top layer, and this layer offers the resistance on the bottom layer. So that is how both the layers are dragging each other. So that is how both the layers are offering the internal resistance between the layers. So that is because of that we find there is a relative velocity. So the relative velocity is very important. So because if there is no relative velocity between the layers, then there won't be any internal resistance. Because of the internal resistance, we are coming across the relative velocity. If there is no internal resistance, then relative velocity will be 0. So since we have a internal resistance, nothing but viscosity, so because of that relative velocity comes into the pictures. So now we have to understand one thing called this shear stress. So shear stress, let us see in a simple way. Relative velocity plus viscosity, nothing but the viscosity, we define it as the internal resistance between the layers, or internal resistance offered to the fluid flow. So here the viscosity is nothing but the internal resistance. That internal resistance we will measure it in the separate term later. First let us see about shear stress. So shear stress nothing but relative velocity plus viscosity. That is what we call it as shear stress. So this shear stress is very important in fluid mechanics. If shear stress doesn't exist, then the fluid will become purely imaginary, or that nothing but ideal. The fluid will be ideal and also without any resistance. If there is no shear stress, then there is no resistance between the fluids. That is the idea. So shear stress is very important. So if this shear stress nothing but because of the relative velocity, because of the viscosity, if the together relative velocity plus viscosity offers or causes or generates shear stress for understanding. So now the relative velocity nothing but du, we say du, nothing but change in velocity. Then the viscosity nothing but we have to find it, okay, new term. Then the shear stress, we say shear stress is directly proportional to this one. dou u by dou y. Whenever we have this one, if we are taking it in the any reference frame, then what happen, this will be generated, this will be causing the velocity profile. So we know well how the velocity profile is generated. So because of this velocity profile, we can just say that this vertical axis nothing but this y, and horizontal axis nothing but velocity u. So with respect to this velocity profile, we have a different velocities. We have a different velocities, and also we have a different height. So that is actually we call it as this. We can say as the height between these two. We can call it as dy, and this is nothing but we say du. So du by dy. So we used to have a relationship, that means du by dy. Whenever there is a du, then dy also will come into the pictures. That is unavoidable. So this du by dy we call it as velocity gradient. This is velocity gradient, we know well. So this velocity gradient is very important. If the velocity gradient doesn't exist, then the shear stress would be 0. If the shear stress is 0, that we say that there is no relative velocity, and the relative velocity comes because of the viscosity. So that is how we have to relate how this shear stress comes because of the viscosity. So it is very important to understand how the shear stress is directly proportional to velocity gradient. When the shear stress is directly proportional to velocity gradient, when you are equating, so that is how we are putting one constant. That constant we call it as Newton's law of viscosity. So this is what we say that dynamic viscosity. So this is nothing but because of the constant of proportionality, or proportionality constant we can say, because we are equating and then we are putting one new constant, that is what called. So this is okay, this is nothing but Newton's law of viscosity, that is what so the law of viscosity. So this is how the viscosity plays a major role and comes to the Newton's law of viscosity. So if this viscosity doesn't exist, there won't be any relative velocity. If there is no relative velocity, there won't be shear stress. If there is no shear stress, then there won't be this Newton's law of viscosity. So that is how viscosity plays a major role in real fluids.